Hello everyone, my name is Oscar Venegas and today I will be presenting my topic, which is Graph Neural Networks for Mobility and Handover Prediction in Cellular Networks. This presentation focuses on how modern cellular networks can be modeled as graphs and how graph neural networks, or GNNs, can be used to better understand and predict user mobility. The main motivation behind this topic is that mobility management is one of the most important functions in wireless networks, especially in 4G and 5G systems where users are constantly moving and the network must maintain a reliable connectivity. In this presentation, I will first explain the mobility and handover problem and then show why graph-based modeling is a natural fit for cellular networks. Finally, I'll discuss how GNNs can be applied to improve mobility prediction and proactive handover decisions. Let's start. The motivation, why mobility prediction matters. So this slide explains the motivation behind the topic, basically. In cellular networks, users are not stationary. They move continuously as they drive, walk, or travel through different coverage areas, which means the network must constantly adopt those changes. The network must constantly adapt to those changes. As the user moves, the connection often needs to be transferred from one cell to another cell in order to maintain service. This makes mobility management one of the most important functions in cellular systems. So in cellular systems, let's say 2G, 3G, 4G, and 5G, specifically in 4G and 5G, the last 20 years, there are different types of cells. We have macro cells, we have small cells, we have picocells, and all these because of all the use cases that we have nowadays. So that is another point why it's very important the handover or the mobility problem in wireless networks. The reason mobility prediction matters is that handover decisions are not trivial. If the network waits too long to react, the signal from the current serving cell may already be too weak, which can lead to reduced throughput, higher latency, or even dropped connections. If the decision is made too early or toward the wrong target cell, the result may be unnecessary handovers, extra signaling, overhead, and lower network latency. So in both cases, poor mobility management directly affects the quality of the service by the user. This becomes even more important in modern 4G and 5G communication, as I mentioned, because they support applications with much stricter requirements than before. For example, services such as real-time video, autonomous vehicles, industrial automation, and IoT services depends on reliable and low latency connectivity. In these scenarios, even small delays or connection interruptions can have a noticeable impact. This is why predicting mobility in advance is so valuable. If the network can estimate where a user is likely to move next, it can prepare the handover earlier, allocate resources more efficiently, and improve overall performance. This presentation focuses on how graph neural networks can help with this problem by learning mobility patterns from graph-based representation of cellular networks. So, the handover problem in cellular networks. The handover problem is one of the most important functions in a cellular networks, since the entire coverage area is divided into cells, as I already showed in the previous diagram, each served by its own base station. A user device cannot stay connected to the same cell indefinitely while moving. As the user changes location, the network must decide when to transfer that connection to another cell. This process is called handover, and it is essentially for maintaining continuous service during mobility. For instance, I have worked in Nokia and for some operators in the US, and what I have seen is it doesn't matter if it is an OEM such as Nokia or the, I don't know, Dish or Verizon. There is a ton of software capabilities and features only focused on handovers and mobility. Intra handovers, which is using the same frequency, or intra intra and inter handovers. Intra is using the same frequency and inter is using another frequency. Okay, so the difficulty is that the handover decision has to be made at the right time and toward the right target cell. If the handover happens too late, the signal from the current cell will become too weak, which can cause high delay, poor throughput, or even drop the connection. On the other hand, if the handover is too early, if the handover is triggered too early or without a real need, it can create unnecessary signaling overhead and waste network resources. In some cases, it can also lead to what is known as the ping pong effect, where the user is switching back and forth between neighboring cells in a short period of time. That kind of instability reduces efficiency and negatively affects the user experience. As I already mentioned, this problem becomes even more important in modern 4 and 5G communications or systems because of the use cases where the users often expect seamless connectivity while running latency sensitive applications such as video calls, autonomous system, augmented reality, or industrial control. In these scenarios, the mobility management is not just about keeping the connection alive, but also about preserving reliability and quality of service. Because of this, predicting user mobility and identifying the next likely cell in advance can help the network make more intelligent and proactive handovers decisions rather reacting only after signal conditions have already degraded. For instance, one of the main parameters or the main parameter that is considered for the handover is the quality signal to noise ratio, and how strong the signal is. Parameters such as RSRP, RSRQ, RSSI, signal to noise ratio, these are used since years ago, since the introduction of 2G and the mobility problem. But nowadays, with all these new use cases, such as ultra reliable low latency, for instance, drones, which are controlled, via cellular network, then the latency should be less than 1 millisecond. For instance, in 4G, the latency, the 3GPP standard latency for 4G was about 10 milliseconds. Now, for 5G, they reduced the latency to less than 1 millisecond, which is something that is not only, as I mentioned, is not only to keep the link alive, is to meet certain specifications that every single network has to have. So basically, this is the handover problem and why is so important, because people is moving and people expect to have the best service. And not only that, for instance, in telecommunications or in 5G networks, on 4G networks, in any communication system at least, there is this rule of the 4 nines or 5 nines. For instance, for MPLS, which is transport, we have the the five nines. 99.999% of the time, the network should be available, which is the amount of time that your network will have a problem should be very short. For cellular networks, it is 4 nines, but it is still like, for instance, in 1 year, your network can be only affected for a few minutes, not less than that. And during the time of operation, your network should be meet specific requirements enforced by the FCC, at least in the United States. Let's continue with the presentation. Okay, modeling cellular networks as graphs. So this slide explains why graph-based learning is especially relevant to this problem. A cellular network is not simply a collection of isolated users, devices, or base stations operating independently. Instead, it is a highly connected system in which different cells interact through overlapping coverages, user mobility, signal condition, and repeated handover events. And I would like to add another one, which is technologies. So let's say we have two 5G towers. In these two 5G towers, we will have not only 5G, we will have 5G and 4G. So that's another level of complexity, because most of the times you will have to do this handover intra technologies, 4G to 5G, because in order to transition from 4G to 5G, is not possible to switch, to convert all the towers from 4G to 5G from one day to another. So that's why this dual technology exists. And in some cases, for instance, in Mexico, where I come from, you still can see 3G, 4G, and 5G, which is even more complex. But okay, that's another topic. Okay, so because of these interactions, the behavior of one part of the network is often influenced by the structure and activity of neighboring cells, by neighbors, other cells which are in the nearby, in this surrounding, basically. So that is why representing the cellular network as a graph is a natural and useful approach. In these graph representations, nodes can correspond to different entities depending on the modeling choice, such as base stations, cells, or even users. Edges represent the relationship between them. For example, physical adjacency between cells, connectivity between users and serving cells, or historical handover transition observed in the network. This allows us to move beyond a flat view of the data and instead capture the relation structure of the system. This is important because mobility patterns are not determined only by one user's current signal measurement or one cell's local condition. They are also shaped by the surrounding network topology, the neighboring cells available for handover, and the way users typically move through the coverage area. In other words, the context around a node matters just as much as the node itself. By converting the cellular system into a graph, we can apply graph neural networks, which are specifically designed to learn from both node attributes and the connection between nodes. This means the model can capture local information, such as the state of a serving cell, while also learning broader structural patterns, such as common handover paths or relationship between neighboring cells. That combination makes graph-based learning a strong fit for mobility and handover prediction in cellular networks. Okay, I would like to go one step back, and I would like to present some related work about what I'm talking about. So, if you nowadays, most of the operators and OEMs, when I say operators, I'm talking about Verizon, AT&T, T-Mobile, Deutsche Telekom. OEMs, Nokia, Ericsson, Samsung, all of them, they are trying to implement AI in different ways into the network. So, for instance, 6G is a technology that will have AI or artificial intelligence um, from the beginning. So they are thinking to use the AI in order to optimize the network, even the core or the radio part. So AI will be part of the 6G. So this slide briefly shows that the topic is supported by existing literature, and the idea of using graph neural networks in cellular system is grounded in current research. At a broader level, survey papers show that GNNs have become an important tool in wireless and communication networks because many of these systems can be represented naturally as graphs, where nodes may correspond to devices, users, cells, or base stations, and edges capture interactions such as connectivity, interference, adjacency, or handover relationships. That is important for this presentation because it shows that graph-based learning is not being introduced here as an abstract idea, but as a modeling approach that already matches the structure of real communication networks. More specifically for mobility management, a recent paper by González Bermúdez and co-authors propose a proactive all-round mobility management framework based on user cell link prediction. I would like to open a bracket here. So all-RAN means Open Radio Access Network, and it's basically for those people who is not familiarized with 5G or 4G or this wireless world. Basically, they are trying to segregate. So when you see a tower, what ORAN is trying to do is trying to split or segregate the functions in order that, for instance, if you want to use one provider for the function A and another provider for function B and another provider for function C, you can do it. And previously, OEMs such as Ericsson, Nokia, they belong the whole cake, right? So basically, ORAN is Open Radio Access Network. Okay, I close the bracket. So their goal is to estimate the optimal target cell for handover before the handover is triggered, which directly connects to the mobility prediction problem discussed in this presentation. The paper compares two GNN models and evaluates them using an anonymized real-world dataset together with a synthetic dataset generated with Keysight X-ATA emulation tool. The results show that GNN-based models are able to capture the dynamic and graph structure nature of cellular networks, which makes this work a strong and very relevant example for my topic. In addition, early work on the next cell prediction showed that forecasting the next likely serving cell can support better handover management and more efficient resource allocation. That early line of work is useful because it provides the mobility prediction background, while the newer GNN-based work extends the idea by explicitly using the network structure in the learning process. So, overall, the literature suggests that combining the graph-based modeling with mobility prediction is both relevant and increasingly important for modern cellular networks, especially as networks become more complex, dynamic, and data-driven. Okay, uh, why neural networks? I would like to go more in detail about trying to answer this question. So, graph neural networks are such a strong fit for this problem in many traditional machine learning approach. Each sample is treated as if it were independent from all other networks. That assumption can work well in problems where the data points do not strongly influence one another. However, in cellular networks, that assumption is not very realistic. Cells are connected to neighboring cells, users move across those cells over time, and Handover decisions are directly influenced by those relationships. Um, in other words, the behavior of one of the part of the network often depends on what is happening in the surrounding parts. This is exactly the kind of situation where graph neural networks become useful. GNNs are designed for structured data that can be represented as a graph, where nodes and edges capture both entities and their relationships. Instead of looking at one node in isolation, a GNN updates the representation of that node by combining information from its neighbors. This allows this allows sorry, the model to learn not only the local features of a particular cell or user, but also the surrounding network context. For example, a user's future handover is not determined only by the current signal value, as I already mentioned. It may also depend on which neighboring cells are available, how those cells are connected, and how users typically move between them, and what the recent handover history looks like. This is why GNNs are especially relevant for mobility prediction. Mobility and handover behavior are influenced by the broader graph structure, not just by one isolated measurement at a single moment in time. Excuse me. A GNN can be captured both the individual properties of nodes and the dependencies between them, which makes it better suited for model how movement actually happens across the connected cellular networks. This is also important because handover decisions are inherently relational. The network is deciding not only the state of the user, but how that user transitions from one part of the network to another. By using graph neural networks, we can represent those transitions more naturally and potentially make predictions that are more robust, more context aware, and more useful for proactive mobility management. Okay, possible inputs and prediction targets. What kind of information a graph neural network model will be used and what it will try to predict in the context of mobility and handover management. Since this the representation Since this presentation is conceptual, I'm not going to use a specific dataset or running a real experiment, but in a practical implementation, the model would rely on several types of network and user-related information. For example, one important input is the current serving cell, which tell us where the user is connected and the present moment. Another is the set of neighboring cells, because those representations the most likely candidates for a future handover. The model could also use signal quality measurements, as I mentioned, such as the RSRQ, or signal to noise ratio. Since these metrics provide information about the radio condition experienced by the user and the potential quality of the nearby cells. In addition, recent movement history is very important, because user mobility often follows patterns over time rather than happening randomly. This history might include previous visited cells, recent handover events, or direction and speed information when available. In a graph representation, this information can be attached to either nodes or edges depending on what it describes. For instance, a cell may have a node features such as signal statistics, load, or location, while an edge may capture a relationship such as adjacency between cells or a historical handover transition. If users are also represented as nodes, then their mobility state and measurement history can be included there as well. This flexibility is one of the advantages of graph-based modeling, because it allows the problem to reflect the actual structure of the network instead of forcing everything into a flat input vector. The output of the model can also vary, depending on the objective. One possible output is the next cell prediction, meaning the model estimates which cell the user is most likely to connect to next. Another is the probability of handover, which helps determine whether a transfer is likely to happen in the near future. The model might also identify the best target cell among several candidates, which is useful when multiple neighboring cells are available. In some cases, the system could even estimate the risk of handover failure, which would help the network avoid poor decisions before they affect service quality. The key idea is that the model does not only describe the current state of the user, but tries to anticipate what is likely to happen next. That predictive ability can help the network act earlier, prepare resources in advance, reduce unnecessary handovers, and improve overall mobility management. So this slide connects the data side of the problem with the prediction side, showing how GNN can turn cellular network information into more proactive and intelligent handover decisions. Okay, this slide summarizes the overall workflow of how a graph neural network can be used for mobility and handover prediction in cellular networks. The idea is to start from raw network and user-related information, then transform that information into a graph representation, applying a GNN model, and then use the predictions to support smarter mobility management decisions in the network. Starting from the left, the first stage is input data. In real cellular systems, the model would rely on several sources of information. One example is the current serving cell, which tells us which base station is currently connected to the user. Another important input is the set of neighbor cells, because handovers usually occur between cells that are geographically or operationally related. This model could also use the traditional measurements that are being used for years for handovers, such as RSRP, RSRQ, or signal or SINR, signal to noise radio. I would like to open a bracket here. So basically RSRP and RSRQ are measured on the handset, on the UE, and it's basically, it tells you how good or bad your signal is. RSRP means reference signal receive power. Um, yeah, so let's continue. So all this information will provide data about the radio quality and help estimate whether the user is likely to remain in the current cell or move to another one. Finally, mobility history is important because user movements is often not random. Recent trajectory, previous handovers, or movement direction can help the model identify future handover behavior. The second stage is graph construction. This is where the problem becomes especially suitable for graph-based learning. Instead of treating all measurements as isolated inputs, we will represent the cellular environment as a graph. In this graph, the nodes can represent cells, base stations, or even users, depending on how the system is modeled. The edges represent relationships, such as adjacency between cells, historical handover links, or connectivity patterns. This graph representation is powerful because it captures the structure of the network and the interactions between its components. So, in other words, the model does not only know the features of one cell or one user, it also knows how the elements are related to the rest of the system. The third stage is the GNN model itself. Once the graph is built, the graph neural network processes it by combining node features with connectivity information. A key concept here is often called message passing or neighborhood aggregation. This means that each node updates its representation by incorporating information from its neighboring nodes and edges. For instance, a cell can learn not only from its own signal measurements or load, but also from other characteristics of nearby cells and the movement patterns between them. This makes GNNs especially useful for wireless communication because mobility and handover decisions depend on relationships across the network, not just one isolated observation. So, the GNNs learns patterns and connect local node information with the broader network structure. The fourth stage is prediction outputs. After processing the graph, the model can generate different kinds of prediction depending on the design goal. One possible output is the next cell, meaning the cell the user is most likely to connect to next. Another possible output is handover probability, which estimates how likely it is what a handover will occur in the near future. The model might also identify the best target cell, which is useful if several candidate cells are available. In addition, the model could estimate failure risk, meaning the probability that a handover may fail or lead to poor performance. These outputs are valuable because they move the network from reactive operation to predictive operation. The final stage is network action. The purpose of the prediction is not just to generate numbers, but to improve network behavior. If the system can anticipate where the user is likely to move next. It can support proactive handover, meaning the network can prepare resources in advance and reduce interruption time. It can also lead to improved mobility management overall by reducing unnecessary handovers, lowering the chance of drop connection, and improving quality of service. This is particularly important in 5G and the future 6G systems, where applications such as autonomous vehicles, immersive media, and industrial automation require very reliable and low latency connectivity. So, the main takeaway from this slide is that the pipeline transforms raw cellular mobility information into predictive intelligence that can support better handover decisions. It begins with data, builds a graph representation of the network, applies a GNN to learn from both features and relationships, produces predictions, and then uses those predictions to improve how the network manages mobility. Okay, challenges and limitations. On this slide, I would like to highlight what are the challenges and limitations that even though graph neural networks are a very promising approach for mobility and handover prediction, there are still important challenges when trying to apply them in a real cellular systems. One major issue is that cellular networks are highly dynamic environments. Users move constantly, traffic demands changes over time, and the relationships between cells can also evolve, which means the graph is not fixed or static. Unlike many standards, standard graph learning problems, here the underlying structure may change continuously as the network state changes. Another challenge is the quality. Real network data is often noisy, incomplete or unevenly collected across the system. Measurements may be missing, delayed, or affected by practical issues in the radio environment. In addition, operators may have limited access to certain types of data, especially when information comes from different vendors, different interfaces, or different parts of the network. This makes it difficult to build a clean and consistent dataset for training and evaluation. There is also a modeling challenge because the performance of the GNN depends on heavily how the graph itself is constructed. We need to decide what should be represented as nodes, whether those nodes are cells, base stations, users, or some combination of them. We also need to decide what kinds of relationships should become edges, such as physical adjacency, overlapping, coverage, historical handovers, or signal-based similarity. On top of that, the choice of features matters a lot because the model can only learn useful patterns if the input representation captures the right network information. Scalability is another important limitation. Real cellular networks can include a very large number of users, cells, and interactions. So the graph may become very large and computationally expensive to process. That matters even more if the prediction needs to be made in real time because mobility management decisions often cannot tolerate long delays. A model that performs well offline may still be difficult to deploy if it is too slow or too resource intensive for a live system. Finally, deployment in operational networks requires trust in the model. Engineers need systems that generalize well across different network conditions, user behaviors, and geographic environments. They also need some level of interpretability, because network operators usually want to understand why a model is making a particular recommendation, especially when that recommendation affects live service. In other words, accuracy alone is not enough. The model must also be robust, scalable, explainable to some extent, and fast enough to support actual mobility management decisions. So while GNNs are very promising, this slide shows that there is still a significant gap between having a good research idea and deploying it reliably in a cellular network. Okay, in this slide, I would like to summarize the main message of the representation and also give some ideas of how the new technologies or the new ideas are helping to integrate not only GNNs into cellular networks, but all kind of models into 5G networks and 6G networks. So the cellular networks are not just collections of isolated users or base stations operating independently. Instead, they are connected systems with rich and constantly evolving relationships. Cells are linked through adjacency and overlapping coverage areas. Users move between them, and handovers create patterns of interactions across the network. Because of this, graph-based modeling is a natural fit for representing how mobility actually occurs in a cellular environment. This is why graph neural networks are such a promising tool for this problem. Unlike traditional methods that mainly focus on individual observations, GNN can learn from both the features of individual nodes and the structure of surrounding network. This means they can capture not only local information, such as condition of serving cell or the recent behavior of the user, but also broader context, including neighboring cells, likely transition paths, and historical mobility relationships. For mobility and handover prediction, that is especially valuable because network decisions depend on connectivity and interactions, not just one measurement at one point in time. So, throughout this presentation, I show how a cellular system can be represented as graph, how a GNN-based pipeline can support prediction, and how recent research has already started applying these methods to mobility management in practical wireless network settings. In other words, not only a theoretical idea, but a research direction that is already being explored in modern cellular and O-RAN systems. So if you search AI and 5G, you will find a bunch of news where operators are trying to implement AI in order to optimize the operation of the network. For instance, in the previous slide, I mentioned the challenges. Among these challenges are that the 5G, 4G, the cellular networks itself are very complex and dynamically. So in 6G, there is this concept of digital twin. So the digital twin will be able to will be help to implement ideas like this one, because a digital twin is a digital representation of a physical system where the digital twin ingests real data from the physical implementation. So the AI in general, the machine learning is a reality in wireless networks, and at the same time, there are still some important opportunities for the future, as I already mentioned. These include improving graph construction methods, handling more dynamic and large-scale network conditions, supporting real-time operation and integration these models into 5G practical and open RAN architectures, which is the digital twin 6G, which is it's getting a lot of hype for 6G. So overall, the main conclusion is that GNNs offer a strong direction for making future cellular mobility management more intelligent and proactive by combining graph-based modeling with learning-based prediction. They have the potential to improve handover decisions, reduce unnecessary disruptions, and help networks respond more effectively to the user mobility. So these are my references. Thank you so much for your attention.